This is Bill Farmer again. Welcome back to McMaster University course, Computing and Software 701, Logic and Discrete Mathematics. Last time we were working our way through the topic Basic Mathematical Concepts, and we were talking about cardinality, and I mentioned these two theorems. And the first theorem, we're going to prove both parts. The second theorem, which has a rather involved proof, we're not going to give. Okay, so let's look at these first two. The first part of this theorem says that the natural numbers is equipolant with the rationals. That means there's a bijection between the two. And the second one, which is due to Georg-Cantor, says that the natural numbers is not equipolant to the real numbers. And notice all three of these sets are infinite. So what we're going to do is I'm going to show something a little different. I'm going to show that the natural numbers is equipolant with the positive rationals. Now, it's pretty easy to see that if the natural numbers is equipolant with the positive rational numbers, it's equipolant with all rational numbers. So here's how I'm going to do it. I'm going to write down a big infinite grid of all the positive rational numbers. So here I'm going to have 1, 2, these are going to be the natural numbers. And here I'll have the same. And in these, we can think we have this grid here. But it's an infinite grid. So what I want to do is I'm going to use a different color here. I'm going to put in so this is 1 over 1, 1 over 2, 1 over 3, 1 over 4, and so forth. So I can fill in this whole grid with these fractions. This is 2 over 1, 2 over 2, 2 over 3, 2 over 4, 2 over 5, and this is 3 over 1, 3 over 2, 3 over 3, 3 over 4, 3 over 5, and this is 4 over 1, 4 over 2, 4 over 3, 4 over 4, 4 over 5. So you can see if I continue filling out this infinite grid, I will have written down every positive fraction of natural numbers. Now, of course, this is not exactly the same thing as the positive rational numbers because, for instance, we have here 1 over 1 and we have 2 over 2. These are the same rational numbers. So the rational numbers have representations that can occur more than once. Okay, so in order to show what we have up here, I need to show you how we can basically count out all the rational numbers in this grid. And this is how I'm going to do it. I'm going to start here, and then I'm going to go to here, and then I'm going to go to here, then I'm going to go to here, and then I'm going to go back up this, and then down this, like this. And if you think a moment, if I count them out, so I have 1 over 1, that's 1. I have 2 over 1, that's 2. I have 1/2, that's here. Then I have 1/3. And then I'm going to skip this one. Then I have 3. Then I have 4. Then I have 3/2. and so forth. So this is really a pictorial proof that shows that I can count out the positive rational numbers, and that shows what I'm trying to prove right up here. That shows that the natural numbers are equipolant with the positive rationals. Okay, now that may be a little bit surprising because you may think, well, there should be a lot more rationals than there are natural numbers, but it's not the case. In terms of size, they are the same size. Okay, so what I'm going to do next is we're going to prove, well, hey, let me go back. We're going to prove what's right here. We're going to prove this result. The natural numbers is not equipolant with the real numbers. Okay, so what I'm going to do is I'm not going to actually prove that. I'm going to prove something a little different. I'm going to say the natural numbers is not equipolant. Now, wait a second, let me just go back. Yes. I wanted to make sure I wrote it down right. Okay, so the natural numbers are not equipolant. Now I'm not going to look at all the real numbers. I'm going to look at the real numbers between 0 and 1. And I'm going to show you that the natural numbers are not equipolant with the real numbers between 0 and 1. Now if I could show that, I can show they're not equipolant with all the real numbers because that's a bigger set. Okay, so let's think about these real numbers between 0 and 1. So if we have our number line here, we have 0 and 1. And if we write these down in a binary fractional way, instead of writing them as decimal fractions, let's write them as binary fractions. 0 here is going to equal, I should say, infinite binary expansions. It's going to be with an infinite number of zeros. And 1 here is going to be 0, and then we're going to have an infinite number of 1s. So the smallest number is 0. Our binary expansion is going to be all zeros. Our biggest one is going to be 1. Our binary expansion is going to be all 1s. And then all the other real numbers will be in between here. So for instance, I could have a real number like this. That's going to be somewhere in between. Okay, so what I'm going to do is, let's assume that the natural numbers is actually equipolant with this. What that means is I can list out all the numbers between 0 and 1 in binary. So that's what I'm going to do. I'm going to say the first one I'll call A0. And A0 is going to look like, no, maybe I won't call it A0. Let's call it, no, I guess A0 is okay. So I'm going to write the digits. It's going to be, first one will be 0, and then the next digit will be, I'll write like this, B00, 0, and the next digit will be 0, and the next digit will be like this. So forth. And then A1, it's going to look like this. Oops, this is a 1, sorry. And so forth. And then A2, we just continue this way. Now all these B's, they're all going to be either 0 or 1. Because in base 2, those are the only digits we have. So these go infinitely this way and infinitely this way. Okay, so because I'm assuming that the natural numbers are equipolant with the real numbers between 0 and 1, including 0 and 1, then I know I can count out those numbers. Because equipolant means there's a bijection. So if there's a bijection, I basically can map. I can map here. So the mapping is basically taking n, and I'm mapping it to a sub n. Okay. So now what I want to do is define a number. And this is how I'm going to define. I'm going to call it, I'll call this number C. Actually, first I need some notation. Here's my notation. Let's say if we put a bar over B, that equals 0 if B is 1, and A equals 1 if B is 0. Okay. So now I'm going to define C, and I'm going to show you what I'm going to show you what it is. It's going to be, the first will be 0, and the next will be B00 bar. And the next one will be B11 bar. And the next will be B22 bar. And these B00s, B11, B22, they come from these up here. Okay. Now the question is C on that list? It better be on the list, because I'm assuming that the natural numbers I'm assuming that this is a list of all the real numbers between 0 and 1, so it better be on the list. But let's check. Could it be, so we can ask the question, is C equal to A0? Well, let's go up and look at A0. The first digit in A0 is B00. But if we look at C, the first digit is B00 with a bar. So whatever the digit is for A0, it's not going to be the same. So if A0 is 0, C is going to have 1 here. If A0 has 1, this C is going to have 0 here. So this is not the case. It cannot be A0. So let's ask the question about A1. But if we go up to A1, we see that the second digit right here is B11. We have B11 bar. Same argument. Can't be this. It can't be any of them. And that's because if we look at what we have here, basically what we've done is we've taken the diagonal along here and then we flipped all the bits along here. Because we flipped all the bits or the digits along the diagonal, it can't be on the list. And as a result, we have a contradiction. So C is not on the list, which is a contradiction. So therefore, n is not equipolant with the real numbers between 0 and 1. Now this kind of argument is called a diagonalization argument. And it's due to Georg Cantor. who was working in the end of the 19th century, and he is really the father. He's one of the founding fathers of set theory. Okay, so let's go back to our slides here. We're going to go to a new subject, mathematical structures. So a mathematical structure is just a set of values, mathematical values, that are structured in some way. They have a structure. Now, I'm going to give a definition which will make this much more precise. It's going to be a pair here, and it's going to be a pair of two things. Script D, script A. And script D is a non-empty finite set of domains. So domains are just sets, but we're calling them domains because we're going to be taking values from these sets. So script D is a bunch of these domains, but we're always going to assume that the number is finite, and we're also going to assume that the domains are non-empty. And then script A is just going to be a set of distinguished values. These are just going to be members of the domain, or they could be true and false, or they could be constructed from these domains, constructed from the domain of false and true, and the domains in script D. And usually, in most mathematical structures, the distinguished values are going to be elements of the domains, functions over the domains, or relations over the domains. Okay, so that's what a mathematical structure is. We're going to look at a lot, but we're going to use a simple notation that suppose this is our set of domains, and suppose this is our set of distinguished values. When in that case, notice both are finite. We will often write our mathematical structure like this. We'll just list out the domains, list out the distinguished values. Okay, so let's take an example. This is an example of a complete ordered field. It's right here. It's written in this as this tuple. And there's only one domain. It's a single domain. Most structures we deal with usually have either one domain, sometimes two domains. They could have many domains, but usually one or two domains at most. And these are the distinguished values. And it turns out 0, and 1 are members of R. Plus and times are functions like this. Binary functions over R. And minus and the multiplicative inverse, they are functions that take a single input. Excuse me, I made a mistake here. A single input. And return a real number. And then finally, we have equals and less than, and they are relations, binary relations over the real number. Okay, so this is an example of a mathematical structure, and it's important to note here that this is a very important mathematical structure. It's the structure of the real numbers. We'll be talking about this over and over again. Okay, so what we're going to do in much of the rest of this topic is do a survey of different kinds of mathematical structures. And the real important examples are number systems. We've already talked about those. Orders, we're going to go in some depth about orders, different kinds of orders like partial orders, total orders, well orders. Then we're going to look at algebraic structures, lattices, graphs, and trees. And it's important to note another very rich collection of mathematical structures are abstract data types that are used in computing. And these are things like strings, lists, streams, arrays, records, stacks, queues, and so forth. Okay, so we're going to stop here. And next time we are going to continue with looking at specific specific mathematical structures which are orders. Thank you very much. See you next time.